Welcome, everyone, to this session of the Geneva Symmetry Group. I am very pleased to welcome Matěj Krátký, I hope I pronounced this correctly, who is visiting us from the University of Oxford. Matěj is a prospective PhD student at the University of Geneva, so I hope that he will be coming to Geneva to start his PhD studies in the fall. So far he's studied some mathematics at the Charles University in Prague, in his native Czech Republic, before then going to the University of Oxford, doing a BA degree in philosophy and physics, and now finishing up a master degree in mathematical and theoretical physics. And today he will be talking about what does the Aharonov-Bohm effect teach us about physical possibility. Please, Matěj.
Thank you. Well, actually, thank you to everybody for welcoming me here. I'm very happy about this opportunity to come here and to speak in front of you. It's also a kind of first time that I'm speaking in this seminar-like setting, so bear with me, but also do ask the difficult questions. That's very important. Indeed, I will be talking about the Aharonov-Bohm effect, and I will be trying to make a kind of special twist on the literature which already exists. So the plan is roughly the following. First, I'm going to talk about what it means to give a proper dynamical account of the Aharonov-Bohm effect, only to then interpret this setup. And lastly, I'm going to develop this kind of skeptical stance towards the whole business and see if it's justified, because with skepticism it's always a double-edged sword. We never want to be too skeptical, but we also don't want to be too forgiving. So kind of evaluating that, and then maybe some interesting conclusions at the end. Perfect. So the literature on the Aharonov-Bohm effect so far has consisted of two main strands. On the one hand, there's the debate about ontology, where the Aharonov-Bohm effect has been viewed as a kind of invitation to debate the ontology of electromagnetism, precisely because the kind of commonly accepted wisdom that the F field or the electric and magnetic fields are fundamental seems threatened by what we will soon call the Aharonov-Bohm effect. Specifically, the dilemma seems to be that either the F field has to act non-locally or it has to be non-fundamental. And indeed, even the Aharonov and Bohm themselves in their seminal paper say that it would therefore seem natural at this point to propose that in quantum mechanics the fundamental physical entities are the potentials, that is the A field, while the fields are derived from them by differentiations. So that would seem to be what people took to be the natural reaction to the setup. And indeed, then many ontological accounts kind of reacted to this, and that's the whole ontology debate. On the other hand, more recently, people started studying the idealizations involved in formulating the Aharonov-Bohm effect. So we are going to talk more about this later, but the effect involves an infinitely long solenoid, which is perfectly impermeable to the incoming electrons. So what do these idealizations imply for the dynamics or for the explanation of the effect? And have we actually observed the genuine Aharonov-Bohm effect in the laboratory? So that's the concern of the more recent strand of literature. And what I would like to do is to make a kind of connection between these two strands of literature. Take inspiration kind of in the idealizations debate and try to show that it perhaps undermines some of the motivations for the ontology debate, perhaps showing that there is no dilemma for F-field realism in the end. Good. So the Aharonov-Bohm model. The setup is very simple, perhaps familiar. We start with the normal double-slit experiment, and we modify it by placing this infinitely long, perfectly impermeable solenoid kind of in the way of the electrons. And as it turns out, I mean, once we start sending current into the solenoid, the interference pattern, the original one, gets shifted. Why is this interesting? Well, once we make these idealizing assumptions, namely that the solenoid is infinitely long, that all the magnetic field is perfectly confined within the solenoid, and that the electrons cannot enter the solenoid, it would seem that an observable effect has been produced without the electrons ever kind of coming into contact with the magnetic field. So that's kind of the punchline of this setup, because the electrons are confined to the outer region while the magnetic field is confined to the inner region. This is not the only setup that we can think of. Experimentally, when people try to implement this, they have worked with, for example, a toroidal solenoid, or maybe just taking two finitely long solenoids, because of course that's more experimental. It's easier to implement that experimentally, and that will actually become important later. Good, so let me just make a mild proposal about semantics, and I don't think anything very important hinges on this, but it will bring some clarity, I hope, especially when people argue about the Aharonov-Bohm effect being or not being observed. Let me refer to the Aharonov-Bohm model. Let me denote by Aharonov-Bohm model precisely the kind of setup which I presented on the previous slide. So a mathematical model of the double-slit experiment scenario, which has precisely these idealized assumptions, or maybe a similar set of idealized assumptions in the case of the toroidal effect or something else. And by the Aharonov-Bohm effect, I'm going to denote like the genuine observed experimental shifts observed in the laboratory, or maybe somewhat informally I will use that to kind of denote the whole debate that we're debating right now, but that will be truly informal. Good, so this means that by definition, the Aharonov-Bohm effect has been observed in the laboratory, but arguably it's the Aharonov-Bohm model which has all the interesting kind of exhibits the non-local features and is more interesting to philosophers. Good, so now I pose two questions. Does the Aharonov-Bohm model represent a physical possibility? That's the first question I will tackle. And the second one, does the Aharonov-Bohm model genuinely pose a dilemma for F-field realism? Good, so now let's talk about the dynamics. It turns out that like a proper dynamical analysis of the Aharonov-Bohm effect is actually, involves certain mathematical niceties which sometimes don't get mentioned, maybe because physicists tend to kind of sweep these issues under the rug, but I think we should attend to them in this context. For one, it turns out that the natural Hamiltonian that one would propose for the Aharonov-Bohm model, which is exactly this one, is not a self-adjoint operator when it acts on the space of smooth functions with compact support in the outside region, which is dense in L2. That's the natural space of wave functions, of course. It is not self-adjoint. However, we can make it self-adjoint by imposing certain boundary conditions on the wave functions. So indeed, Aharonov and Bohm imposed the Dirichlet boundary condition at the solenoid, making the wave function go to 0. And that would define a new Hamiltonian operator and work with that. But they didn't offer any justification. And arguably one could kind of implement the intuitive idea of impermeability by imposing any other boundary conditions. So for example, the von Neumann boundary conditions or the Robin boundary conditions, they would all make the probability current at the solenoid vanish. So they would all kind of implement this idea of impermeability equally well. And these different boundary conditions, they correspond to different self-adjoint extensions of the original Hamiltonian, and indeed would produce different observable effects. So in some sense, the challenge is, can we justify this choice of Dirichlet boundary conditions? And it turns out, indeed, we can. So let's imagine a more realistic sequence of systems. So we start with a solenoid of finite length, and we take it to be, for now, perfectly permeable to the particles. So the configuration space for the particles is simply connected, that is hence the entirety of R3. If we denote by chi L the characteristic function of the solenoid, that is functions which is 0 outside the solenoid and it's 1 where the solenoid is located, we can implement the impermeability assumption by adding a potential term to the Hamiltonian. labeled by integers n. So then we have a sequence of models which are on the one hand labeled by this integer and on the other labeled by length of the solenoid. And we have a corresponding family of Hamiltonians. So that's exactly this one. And here AL would be the magnetic potential of a finitely length solenoid of length A. So it would just be the natural Hamiltonian to propose for this more realistic systems.
So n goes to infinity though? Or
It's going to, yes, it goes to infinity right here. Yeah. So, yeah. If we now take the limit as n and l, and both n and l go to infinity, well, the Oliveira and Pereira, they show that actually this converges to the original Aharonov-Bohm Hamiltonian with the Dirichlet boundary conditions. And moreover, yeah, the order in which we take the limits doesn't matter, so that's a very, very nice result. And yeah, the sense in which the limit is taken is this strong resolvent sense, which seems to be the natural choice of convergence for self-adjoint operators or something like that. Yeah. Good, so that's, thus we have kind of vindicated the choice of the Hamiltonian which Aharonov and Bohm proposed. Good, so yeah, this is a kind of, this is a picture which schematizes what we've just done. We have kind of a two-dimensional lattice of Aharonov-Bohm models, and in the limit, as we take both of these parameters to infinity, we get the AD model which has all these idealized assumptions that we started with. Good, so let's now try to interpret these models. Before we do that, I would like to make this distinction, which goes back, I think, to Dennis Lemkuhl, between literal and careful interpretations in physics. And I think the context in which Lemkuhl introduces this distinction is the problem of motion in GR. That is, the problem of deriving the geodesic equations from the Einstein field equations themselves. So the question whether they are a theorem or whether they're an independent postulate. Well, there are, I think, two approaches to deriving this result, and Lemkuhl focuses on the so-called vacuum derivation. The problem with the vacuum derivation of the geodesic equation is that it explicitly features space-time singularities, and the material particles apparently are kind of represented by singularities or evolving singularities in these space-times. So it has been maybe rejected by philosophers as kind of unphysical, and Lemkuhl kind of tries to defend it by saying that we should kind of be more, we should interpret these singularities more carefully. So if we just take a literal stance, we reject the model as unphysical, but if we think about it carefully, then maybe we can think about the singularities as placeholders for some more physical particles, or genuine material particles, or non-singular metrics, I think, something like that. To give more examples of this kind of thinking, so take the Schwarzschild solution. Understood literally, that's just a singularity in an empty universe. But if we apply it carefully to a more particular situation, that could represent, for example, the field outside of a very particular stellar object, like the sun or the black hole at the center of our galaxy. One more example, thinking about fluid dynamics, the way we model flow of fluids is by vector fields evolving in time in three-dimensional space, roughly speaking, subject to the Navier-Stokes equation. It would seem that if we think literally about these models, we would be led to believe that fluid is a perfect continuum, which, as we know, it is not. So maybe thinking more carefully about these models, the velocity vector is just some kind of average velocity of the molecules at some point, and it seems more physical way of thinking about these models. Good, so with this distinction in mind, let's try to apply this to the sequence of Aharonov-Bohm models which we've just devised. And I think there's kind of there's two ways that we can think about the representation relation here. So on the one hand, there could be something like a literal interpretation of the Aharonov-Bohm models, where so these M's are the models we've had on the slide with the lattice, or it's a particular subset of the lattice, and these W's are possible worlds which correspond to these models in a very literal sense. There's just an arrow to this world would contain some kind of actual solenoid of infinite length and some finite permeability. And the literalist would claim, well, there's a one-to-one correspondence between the two. If we want to be more careful, though, and if we maybe want to follow the practice of physicists more closely, we would be perhaps led to think that what is actually happening is that the physicists are taking the idealized Aharonov-Bohm model and using it to represent these actual world systems, genuine solenoids, maybe not with infinities here, but maybe some finite length solenoids with finite permeability. That's what the physicists are actually doing. And in particular, the physicists don't seem to be referring to this idealized world at all. That doesn't seem to figure there. So this would be maybe a second way to paint the representation relation. As I just said, I think it perhaps captures better what the physicists are doing. Maybe there's a second question: is it the true representation, or which of these two is objectively better? And yeah, I'm not sure if there is such a matter of fact actually. So maybe we can discuss that question later or postpone it. But I would certainly think that this corresponds better to what physicists are doing. Good. Well, there are people who disagree, I think, with this. So John Earman, in his take on the Aharonov-Bohm effect, first starts by distinguishing two senses in which we idealize in physics. So he says, it seems fair to say, however, that almost all of the attention in the literature on idealizations in physics has focused on one sense of idealization. The target system is an actual system, and the idealization involves intentional use of falsehoods or distortions in representing or modeling the target system. That's the first sense. In the second sense, the target system is an idealization in the sense of fictional system, a system which is compatible with what in the context of inquiry is taken to be a fundamental theory of physics, but which is not realized in the actual world. And while I think Earman is not explicit about this, I take this to be exactly the same distinction that Norton makes between approximations and idealizations, where approximations are propositional falsehoods which we use to describe systems, while idealizations are genuine systems which we use perhaps in the same way, but approximations are propositions and idealizations are systems. There's a reference to a system when we're idealizing. I take Earman in this passage to be saying basically the same thing, but maybe people disagree, and it's a little suspicious that he doesn't make this connection, I think, in the paper. Good. So after making this distinction, Earman makes the following comment. Put simply, he believes that the Aharonov-Bohm model should be understood as an idealization in a second sense. That is, in the sense of Norton as an idealization as opposed to approximation. So he says that the target system in the AB effect is a fictional system, and there is no idealization in the usual sense, as in the first sense. No distorted / false description of an actual world arrangement of magnets and electrons, but rather an accurate and precise description of an otherworldly arrangement. And the reason he gives for believing this is that what draws the interest of physicists and philosophers alike about the Aharonov-Bohm effect is the alleged prediction of quantum mechanics that the behavior of an electron depends on the value of the magnetic flux in circumstances where the electron never enters a region where the magnetic field is non-zero. So appeals to this interest of physicists and philosophers in justifying the Aharonov-Bohm effect being an idealization rather than an approximation. Good. So and I take this. I take Earman to be subscribing to the literal interpretation of MAB, that is kind of to the left diagram, which we had on a couple of slides ago. Yes, and I think I would like to disagree with this for two reasons. One reason I already mentioned, which is that I think the careful interpretation perhaps better captures what the physicists are actually doing with the Aharonov-Bohm effect. And the other reason is what I'm going to argue next, which is that the Aharonov-Bohm world is actually not physically possible. So the Aharonov-Bohm model cannot possibly represent an otherworldly arrangement because that otherworldly arrangement is not physically possible. Good, so let me formulate this as a thesis, the Aharonov-Bohm skepticism. I will argue that the world WAV is not physically possible. And as I'm sure you're aware, rejecting physical possibility is, or debating physical possibility is a lot of what philosophers of physics do, and there's a long-standing tradition of philosophical skepticism about physical possibility. So for one, there's the Leibniz-Clark correspondence, where famously Leibniz uses his two metaphysical principles to attack the physical possibility of certain shifted models of Newtonian theory. Then there is Ernst Mach, who also criticizes Newtonian theory, but from a slightly different standpoint and much later. Specifically, he focuses on the bucket thought experiment and the two globes thought experiment. Much more recently, in the 21st century, there's Harvey Brown in Physical Relativity, where he criticizes Malamant's alleged proof of non-conventionality of distant simultaneity, also kind of being skeptical about this Malamant world and Malamant scenario. And lastly, I think we could also put here Tim Maudlin on the whole argument and his metric essentialism, which kind of rejects certain what people thought to be possible worlds, rejects them based on this principle that space-time properties of space-time points are held essentially. I will elaborate on these to demonstrate what I have in mind. So, for example, with the Leibniz-Clark correspondence, Leibniz writes, "To say that God can cause the whole universe to move forward in a right line or in any other line without making otherwise any alteration to it is another chimerical supposition. For two states indiscernible from each other are the same state, and consequently 'tis a change without any change." So that's appeal to the principle of identity of indiscernibles. "Besides, there is neither rhyme nor reason in it, but God does nothing without reason, and 'tis impossible there should be any here." That's the principle of sufficient reason. "And besides, it would be, again, doni nihil agere, as I have just now said, because of the indiscernibility." Good. What I think is distinctive about this kind of skepticism is that it's metaphysical. It rejects the possibility of these shifted models based on two superior metaphysical principles: principle of identity of indiscernibles and principle of sufficient reason. This is to be contrasted with what Ernst Mach does in his Science of Mechanics, because Mach writes, "All our principles of mechanics are, as we have shown in detail, experimental knowledge concerning the relative positions and motion of bodies, and even in provinces in which they are now recognized as valid, they could not and were not admitted without previously being subjected to experimental test. And importantly, no one is warranted in extending these principles beyond the boundaries of experience." So there is, I guess, a positivist twist to Mach here, but we don't need to make that step. But the difference between Leibniz's skepticism and Machian skepticism here seems to be that Mach is much more epistemic about it. He's worried about the warrant we have in kind of extending our beliefs or extending our inductive beliefs about physical theories. What do they actually warrant? So I think that's kind of a distinction we can make here. Lastly, to mention Harvey Brown and physical relativity. Harvey Brown is concerned with this scenario where the so-called Malamant world, which is this very basically empty space-time with this single material body or single world line, and this is the setup that Malamant uses to do some manipulations and prove that the simultaneity relation could be proven to be unique in some sense. And this is criticized by Harvey Brown quite heavily. He writes that the Malamant world is so utterly different from ours, I think it is legitimate to ask whether it even contains time at all. It is not enough to say that being four-dimensional, the space-time manifold therein has time built into it. We are doing physics, not mathematics. Time at its most fundamental level has nothing to do with change, and change is not an obvious feature of the Malamant world. Perhaps more succinctly, I think this kind of counterfactual expresses very nicely what's going wrong with the Malaman world according to Brown. I think it's fair to say that Brown's skepticism is also metaphysical, although perhaps kind of more local, while kind of the Leibniz's principles were global metaphysical principles. Brown is, I think, concerned more what it means to have time or something like that. So it seems to be more local metaphysical skepticism. And the distinctive feature, which is also important for us in the Aharonov-Bohm effect, is that the Malaman's proof would be kind of no longer valid, or it would no longer work once we start making the model more realistic. For example, we start adding more material bodies, because then, as in kind of the Malaman procedure could be carried out with respect to any of these observers, and there would be no unique simultaneity relation. I think that would be the worry there. Good. So let's try to kind of follow these three paradigms, as it were, in trying to attack the Aharonov-Bohm model. So what are the prospects of rejecting the Aharonov-Bohm world, its physical possibility, based on epistemic reasons? Well, the argument would be something like this. So looking at our theories, electromagnetism, quantum mechanics, they surely haven't been tested well in experimental regimes which corresponds to WAB, that is, these idealized regimes, such as infinitely long solenoids or perfectly impermeable solenoids. And therefore we just can't trust these theories in those regimes. We don't know what would happen. It's too much of an inductive jump, or what warrants this belief in the features of the Malaman, of the Aharonov-Bohm world. I guess the natural question which arises next is what constitutes an experimental regime much more generally. What does it mean that it hasn't been well tested in a particular experimental regime? I offer some suggestions, but I certainly don't have a definitive answer to this question. I do think it's an interesting question, though. Arguably, when we do scattering experiments in particle colliders, physicists oftentimes talk about the energy scales involved, and they talk about kind of expecting new physics, once we increase the energies and stuff like that. So that would seem to be it would seem to suggest that the energy scale of scattering experiments somehow defines an experimental regime, and changing an experimental regime would involve moving along this scale. Moreover, I think this is supported by the viewpoint of the renormalization group, which seems to, or is sometimes taken to suggest that the theories themselves are only valid within certain energy ranges. So, and perhaps in the context of the Aharonov-Bohm effect, we could say that the regimes, experimental regimes, are defined by the length of the solenoid, or within certain ranges, or the impermeability within certain ranges. And arguably, we have experimental familiarity only with finitely length solenoids and permeable solenoids. So in that case, the argument would have its way, but it seems that electromagnetism has been well tested with solenoids just simpliciter. So, why wouldn't it just straightforwardly extend? And I think my conclusion is that just the notion of experimental regime is just highly context dependent, depends what we care about in a particular situation. And therefore I wouldn't call this the epistemic argument very successful in this sense. Certainly much more needs to be said about what does it mean not to be well tested in a particular experimental regime. Moving on, could we try rejecting WAB based on metaphysical reasons, kind of like Leibniz? And indeed, I think we can. There's actually several issues. Some of them are quite general to infinite systems. So it's a generic feature of infinite systems consisting of infinite number of degrees of freedom, infinite number of particles, that they exhibit, for example, indeterminism or energy non-conservation. So this, for example, compare that with Norton's model of an infinite spring chain, simply just one-dimensional crystal, point particles connected via springs, solutions which it can be shown that the system is indeterministic by constructing solutions out of a single initial conditions which simply diverge after some finite time. So it's certainly a worry, and arguably indeterminism and energy non-conservation are somewhat unphysical features. So that would be a threat certainly to physical possibility of WAB. Maybe before I carry on, I should say that I don't take any of these to be, or any of the issues that I'm going to present as kind of definitive knockdowns, but maybe together they paint kind of a persuasive picture of why the physical possibility of WAB is doubtful. Good. And of course, relating to this infinite system worry, one could immediately object that, for example, the toroidal version, which concerns only finite solenoid, which is shaped as a torus, is immune, and indeed that would be correct. The next worry is very specific to the Aharonov-Bohm model. Arguably, if the solenoid is infinite, it must have infinite resistance. So how could it possibly sustain the current for any finite amount of time? Doesn't seem to be possible, actually. And of course, maybe we could try to get out of this once again by having a superconducting solenoid or something of that sort. But note that in that case, the resistivity just needs to vanish exactly. It needs to be zero proper, because if it's not exactly zero, then the infinity kind of outweighs that, and the argument doesn't go through. So yeah, actually, yeah, one would, I think I'm not actually sure if the superconducting solenoid would work in that case, because arguably it's hard for something to be exactly zero, but yeah. Wonderful. And last worry, maybe the most important one, because it applies also to the toroidal case, is worry about infinite potentials and their unphysicality. So first of all, there's a purely formal worry, and that's if a potential diverges at a point, it is simply not defined at that point. So if we assume some kind of naive correspondence between possible potentials and smooth functions on some kind of background space, it would seem that infinite potentials are just not admissible potentials. So that's, but arguably that's somewhat formal. Maybe there is a precise mathematical sense of construing infinite potentials, perhaps some kind of delta functions or something like that. But if we start thinking about potentials as distributions rather than functions, we should just be very careful, because the distributions don't have the same algebraic properties as functions, right? For example, we cannot multiply two distributions together easily. So yeah, it's a formal worry, but it's a worry I definitely had in relating to infinite potentials. Second of all, there's the worry of how would an infinite potential even arise, giving some finite structure of particles. How could having finite number of atoms which interact by common, potentials, how could we construct an arrangement which would produce an infinite potential barrier? I don't straightforwardly see how we would do that. And lastly, it's a familiar fact that infinite potentials tend to produce discontinuities in the first derivative of the wave functions, and arguably discontinuities are also quite unphysical. Good. So, as I said, I'm not sure if any one of these objections is a knockdown, but maybe together kind of they paint a picture of that something is going wrong in WAB. It's not physically possible. Moving on. Lastly, maybe we don't have to reject physical possibility of WAB, although we just did, and still kind of get our way with defending F-field realism. So, kind of answering to the second question, which I outlined at the beginning. So, let's define a sequence of propositions, which I label by n once again, which says that in m infinity n, the F fields acts locally on the incoming particles. And indeed, this is the case for all the realistic models, because the configuration space is the entirety of R3, and the solenoid is finitely long. So this proposition would be true of these models. We can think of these propositions as kind of expressing some kind of property which these models have. And well, it's easy to recognize that if we take the limit of these properties, the limit property disagrees with the property of the limit system, which is the Aharonov-Bohm model itself, which is that's a distinctive feature that something is going wrong. So, for example, Norton speaks of these cases. He says that in these cases the infinite limit system fails to provide an idealization. That's what Norton says about this case. And I mean, strangely enough, Earman, connecting to that, says that an effect should be dismissed as a mere artifact of the approximation if it disappears when the approximation is made realistic. But of course, Earman speaks about approximations, so that would be idealizations in the first sense. So he doesn't take this to undermine his own position. But I think I've tried to argue that the Aharonov-Bohm effect should be understood as an approximation. So in that case, using kind of this own Earman's own principle would seem to suggest that the feature of the Aharonov-Bohm model should be dismissed as mere artifacts of the idealized setup. Good. So this kind of concludes my case for defending F-field realism, answering kind of question 2. I would like to mention also some harmless idealizations involved in the Aharonov-Bohm effect. Harmless in the sense that they don't seem to be threatening to the physical possibility, or they seem to be maybe present in all other kinds of physical systems. So firstly, there's what Earman calls the bastardized theory, which is that the AB model, as we construed it, uses this strange combination of quantum and classical treatment, where the incoming particles have their wave functions and they're treated in a quantum way, while the electromagnetic field is purely classical. And Earman doesn't like this, especially when trying to resolve issues about locality and non-locality. Once again, I'm not sure I agree with Earman on this. It would seem that the Aharonov-Bohm effect just makes perfect sense the way it is phrased. Why should we, and as such, it would perhaps deliver some wisdom about ontology or locality in electromagnetism or in classical electromagnetism. Why should we, go to QED to discuss this? I don't see any reason. And indeed, I think this is also what Dougherty says when he talks about QED as applied to the Aharonov-Bohm effect, and concludes that, well, that the Aharonov-Bohm effect is not really interesting to QED, or the Aharonov-Bohm model is not really interesting in QED, because QED quite independently privileges the ontology of the principal connection, which is one of the ontological views in the ontology debate. So in this sense, the Aharonov-Bohm effect wouldn't have the same power, wouldn't have the same push. Good. And then arguably, as always, there is noise. So for example, high energy particles coming from space, or interference with radiation from outside sources, but that seems perfectly normal. There doesn't seem to be anything unphysical, at least to me, with these idealizations. So to conclude, let's just recall the questions I posed at the beginning and the answers we've given. So the answer to the first question, does the Aharonov-Bohm model represent a physical possibility? I think I would like to answer that insofar as it is taken to represent the Aharonov-Bohm world, it does not represent a physical possibility, because we have rejected the physical possibility of the Aharonov-Bohm world. However, if we subscribe to this kind of careful interpretation, it could perhaps represent a wide variety of actual world systems. So in that case, the Aharonov-Bohm model would represent a physical possibility. Good. And second question, does the Aharonov-Bohm model pose a dilemma for F-field realism? Well, it seems that if we reject physical possibility of WAP, then the dilemma for F-field realism kind of disappears, because there is no possible world in which F-field acts non-locally. So that's one reason to reject that. And the second reason to reject that would be this limit property business, where the limit property disagrees with the property of the limit system. So I would think these two are actually independent reasons, although maybe we can maybe discuss that later. Good, and I think with this I will conclude the talk. Thank you very much.
The floor is open for questions. I have one to start things. What is a solenoid simplicity?
Solenoid simplicity.
Simplicitor.
Oh, simplicitor. Oh, as in so just solenoids.
But so infinite solenoids are part of that as well. They fall
sure.
under the concept of solenoid simpliciter. And so if we test only finite solenoids, which is what we do in the lab, we actually test a wider class of solenoids, simpliciter, which includes the infinite ones.
Yes, I think that would be the idea, yeah.
But why should we believe that?
I mean, well, I guess in the sense, the way you define that class, right, you would think that if you start doing tests on a particular subset of that class, it would extend to the entire class. I guess in this sense.
Sure, but I mean, there's always a question, of course, what exactly is the class we're considering here. So it's almost like a group kind of paradox.
Okay.
What are the basic concepts on which we actually base our inductions? Inductive generalizations based on our observations in the lab. Yeah. And I think a perfectly respectable case could be made that whatever that class is, and however indeterminate it may be, and however indeterminate it might be for philosophical reasons, it shouldn't include infinite solenoids.
As in, by that class you mean the entrenched class, maybe in the sense of
the class of things we're actually testing, we're actually observing.
Sure.
It never includes infinite solenoids.
Why would you say that?
Well, do you have seen a physics lab which does experiments with an actually infinitely long solenoid?
Sure. I mean, of course not, but
right.
That's not.
Yeah, I didn't expect you to say yes.
Yeah.
In Oxford we have one. But if that's just something that's not going to be on the table to do experiments on, why insist that it's nevertheless part of the concept or the class defined by the concept?
Good. So I think this is just perhaps a little too skeptical, right? So, I mean, imagine all the systems that we've tested our theories on. Would you be suggesting that you're not allowed to extrapolate at all behind this that would seem to be like extreme inductive skepticism, right?
I agree that would be an extreme form of skepticism. There would be something close to sort of the general Humean inductive skeptic now. We wouldn't want to be there. But on the other hand, we always have to be careful how and what we base our inductions. And excluding infinities doesn't seem completely crazy as a start.
I mean, arguably, the one example that Earman runs in his paper is just imagine running experiments on longer and longer and longer solenoids. Wouldn't skepticism about infinity in that case be just what Earman says is just vulgar inductive skepticism in that case? It's just skepticism about the next instance.
No, I mean the worry would be that no, it isn't. Because even if we continue doing that, they're always going to be finite solenoids.
Yeah, good.
Ever longer, but finite solenoids. So whether or not they're finite, as far as that's concerned, we're not approaching infinity in any way.
Yeah, yeah.
But this.
Excellent. Very interesting. Just a question on the relation between models and physical possibilities. So am I right that in your analysis you don't consider the possibility that only part of a model could latch onto a physical possibility? Because I thought you were going to say something like that when you mentioned Cole's distinction between the literal and the careful interpretation. For instance, if you take a vacuum solution, you can think, okay, we can replace the singularity by a star, for instance. And we could say that only part of the vacuum solution is describing correctly part of the physical possibility, but we should not take this as a whole. Have you thought about that, or really? Because in the case of the solenoid, you would think that, okay, we should just consider what's relevant, the piece of the scenario that we like, and then if you want to be a skeptic about this part of the model, you have to show why that the solenoid is infinite, for instance, give us reasons to worry that this part of the solution is latching onto a physical possibility. You see what I mean?
I think kind of I mean, there's certainly these more realistic models that they are readily available, right? We've worked with them. Perhaps the advantage of the idealized model is that it's simpler or something like that. And arguably, the worry that I've discussed is about the world, not about the model. I have nothing against using the Aharonov-Bohm model. I think that's perfectly fine. It's just what we think about it, how we interpret it. And how, yeah.
But do you think that a physical possibility has to be a possible world?
Oh. No. I think, no, that would be too narrow, right? Sorry, so I mean, for one, I mean, there's the thing you just mentioned, that perhaps we can take parts of models. Also, I mean, I think it's something I perhaps should have said, but it's not clear that models corresponds to possible worlds, complete possible worlds at all, right? I mean, perhaps they correspond to parts of them, or maybe because they don't, for example, settle all propositions or something like that. They settle propositions relating to particular subject matter.
So that may mention that the model is not physically possible because of the reasons you gave, but still the relevant part of the model still latching into a physical possibility. You are not worried about that at all?
Sorry, what do you mean by a model being physically possible here? Because the model is a mathematical construction, right? When we talk about physical possibility, arguably that property is ascribed to worlds. So
yeah, but arguably there are relations of correspondence between mathematics we use and the physical world, right? So you could say, like, if you take the space of solutions of physical theory, you may ask what are the which of the solutions are corresponding to physical possibilities, but you can also ask which parts of which solutions of the theories correspond to physical possibilities. I was just wondering whether this second part might well, it might not be showing that you need to say a bit more, but you know the epistemic and metaphysical reasons you gave. You should not only show that they sever the relation between the models and the physical possibilities, but also that they sever the relation between the relevant parts of the models and the relevant parts of the physical possibilities.
could you maybe cash that out a little bit more with which parts or of the models?
I mean, if you take an infinite solenoid, you might say, like, okay, just as with the vacuum solution, you cannot, you should not take too seriously the infinite quantities in your model. That would be the same in this case, but then the question is, are we entitled to be, what are we entitled to? I have no idea with the details. I just think that I was a bit, not really understanding. Yeah, I don't know. I'm confused, I guess.
It seems to me that if what you're saying, that would, if anything, that would seem to threaten WAB even more, right? Kind of on a naive
Okay. Yeah, but what I was saying is that maybe you just reject WAB, but you still think that the lessons, the non-local effect is still real, even though WAB is false.
I don't see how that would.
Physically, it's not latching onto physical possibility as a whole.
Can I ask you something, just to maybe help clarify the discussion? When you say that just a part of the infinite, the model with the infinities, when you say that it may be that just a part of that model actually latches onto reality, do you think about this in a spatio-temporal sense when you say part actually? So, for instance, you just take the double slit screen and the solenoid and the detector screen, and then you go up some way and go down some way. Do you cut out that bit of the infinite model of that actually?
Not only, but yes. Especially spatial probability could be different parameters. It could also be a scale of energy, for instance.
Okay. And then you would say, still the model, according to the model that we use here, which partly corresponds to reality, we seem to have a non-local effect, if we take the field view. And maybe that we still have to take seriously because at least that part of the model does latch onto physical reality. But then I think you rightly pointed out that for a situation where this, what's the word, solenoid? Actually isn't infinite, we do have, apparently, I take from your talk, we do have more realistic models where the length isn't infinite, and it comes out of these models that the effects become local, right? So then I would suggest that if we use the infinite model to represent, or part of the infinite model, to represent that situation where the solenoid is actually finite, then we are not entitled to infer that the non-locality carries over to the physical reality, precisely because we've got models that represent that situation more literally, which seem to show that there is no non-local effect. I guess that's what you were hinting at in your first reply as well.
Okay, I just misunderstood that if you can show that systematically, I think it's
Yes, I think the local effect in these more realistic models, the effect would be local, right? I mean, the magnetic field lines kind of have to curve around, and therefore kind of being in this outside region as well. Arguably, they could be made arbitrarily weak, and in the limit, kind of going to zero. But out of logic of the thing, they should be there, right? Yeah.
So I have, yes, Lorenzo.
So I actually think that the argument you gave is mostly pretty convincing. So
Thank you.
I just had a few questions also because I missed the beginning. So is F realism the proposition that the fields are fundamental and they are not ontologically derivative of the potentials?
That's right. Yes. Yes.
Okay. So it seems that from what I see, too familiar, seems to make a good case that the most common argument that goes through non-locality is not probably a very good argument. One that says, well, if the field were the only thing there is, or were fundamental and there are no potentials, then you would have to act non-locally, and that's bad, therefore there must be no potentials. I wanted to ask you, what do you think of what I think is a more straightforward argument, which would be, well, what do we have in the Hamiltonian when we have the potential? Therefore, whatever you need to write laws, well, that should be real. If you cannot write the laws quantum mechanically only using the F field, but you need to bring in the potentials, then they must be real. You don't want to have them both. I think why have them both fundamentally? Well, you can matrix from the potential, so let's take the potential as fundamental. Just wondering what you think of that argument.
I mean, it's arguably we need to, whenever we're presented with a physical theory, yeah, we can't always take it at face value, right? And indeed, when you look at the quantum Hamiltonian at face value, it has an A field in it. But surely the A field realism has plenty of problems when you dig into it, right? For example, you can construct indeterministic scenarios out of that, right? And there's gauge equivalent potentials which will do the same job. So the A field realism has significant drawbacks, but you only discover that through actually working with the theory and understanding it. So just because something is kind of presented to us in the theory doesn't mean I think we should take it at face value. That, I guess, would be my initial take on that.
I mean, wouldn't it be still a miracle if something was just a computational thing, just sort of pragmatic device that doesn't represent anything? Why couldn't we reformulate the laws to describe the things directly without this pure fiction? I don't know. That for me seems to just a question. For me, that seems to outweigh whatever consideration. I mean, unless the actual theory reason would be that we cannot have a satisfactory theory of the potential. I mean, to take them as real would be contradictory. Would really have to have some really nasty consequence. It seems to me that this would outweigh the other consideration. But I don't know if you have what you're thinking in on.
Sorry, so you're saying something like if the F field was truly fundamental, we should be able to write down quantum mechanics of the charged particle using an F field.
And why not? How could it be that, if that's what the world is, why cannot we just describe what the laws are?
Yeah. I mean, if you do, I'm not sure about this, but couldn't you do some gymnastics, mathematical gymnastics, try to write down the Hamiltonian maybe in terms of the F field and try to invert that relationship? I don't know. Maybe this is just the simplest way to write it. I mean, for example, the Maxwell-Lagrangian, you can write it, it's written in terms of the F field naturally, but if you want, you can write it in terms of the E and B fields, and it works. It's just a more nasty way to do it, but it still works. Wouldn't something like that be possible in this case? Not sure, just thinking about it as a possibility.
I have another question. I go for seconds first, if you go for second. Okay. So about the Leibnizian sort of way of, or path to rejecting WAB as a physical possibility, you considered the first objection there was about this, against infinite systems, that they're physically impossible because they're infinite. And you said one response to that would be to look at the toroidal version of the AB model, which I take it has, I mean, I'm not familiar with that model, but it has the same, or puts the same kind of pressure on an F field realist. Is that
yes, I
case?
think so.
Okay. Couldn't the F field realist then respond and say, I still have a problem, because even though the length is no longer infinite, the impermeability is still assumed to be infinite. That is just as unphysical in the infinite limit, and I therefore also do not buy that version of the AB model.
Wouldn't that be just my third point right here, though?
I guess, yes. Yes.
I think this infinite systems here means infinite, I guess, in extent or in length, or
Yeah, I see. Okay. Yeah, no, I see your point. That's fair enough, yeah. Okay. Yeah. Infinite extent is certainly taken care of in the toroidal version of the AB model. Yes.
Yeah.
Okay. Thank you. Tim.
Thanks. I would like to say that I also think the argument is very convincing in general. First point. Second point, I was interested to hear a bit more about why you say that indeterminism and energy non-conservation are vicious and non-physical features. Is there an independent reason to think that is the case, except that we don't see them with finite systems, or?
I mean, in certain debates, for example, relating to the A field and relating to whole argument, maybe indeterminism is taken as a bias, but arguably, yeah, it's, maybe there should be a debate about these principles. Is that a good principle to impose on this discussion, to see indeterminism as a bias? With regards to energy non-conservation, yeah, I'm not aware of independent reasons, and yeah, I guess you could push me and just say, well, despite exhibiting these features, they are still compatible with the dynamical laws of these evolutions, so maybe in that sense they should be physical. And yeah, no, I think that's right, and maybe that's also why I kind of wanted to take this more as a kind of palette of options. Yeah.
I have a follow-up on that. Isn't indeterminism bad here because it's more like the kind of indeterminism we see with gauge potentials or the whole argument, rather than with like something as we see perhaps in quantum mechanics or elsewhere?
So
and therefore it would be bad?
I think you're right. So the indeterminism as it would be exhibited here would be, in some sense, well, observable maybe. So I mean, the indeterminism we have with respect to gauge potentials is kind of unobservable in the sense that we cannot distinguish gauge equivalent setups. But here, there would be, for example, I mean, we can imagine genuinely distinct solutions, for example, of some kind of material waves propagating in the solenoid. So in this sense, this would be physically distinguishable situations.
So that was my coming to help you would not work.
It backfired.
It backfired. It means, in fact, it would be more like the observable indeterminism that perhaps we have in quantum physics. In which case, I mean, there could still be more general grounds in which to oppose that, right? Because indeterminism is always bad, because we have to deal with probabilities and things, and we'd rather not, right? We have to perfectly beautiful deterministic evolution. And some people have very strong metaphysical inclinations about that. But
in this case, it would probably mean that we don't have the probabilities, right? We have nothing to say about the probabilities.
But then it would be really bad, because at least in quantum mechanics we have probabilities.
Yeah.
We can do statistics.
But it's not clear whether that's a reason to think that the indeterminism isn't real, or a reason to think that our theory is, in this sense,
would be failure of the theory.
Oh, yeah. It might be real, I agree, but it would be undesirable, for sure.
So let's not believe in it.
Yeah, I don't like it. Let's ignore it.
Actually, I will follow up on myself. Let me, I don't know. My impression of the discussion so far is that everybody in this debate comes with some, essentially, criteria of theory choice, a priori criteria of theory choice, such as, well, all else being equal, we should have better have a theory which is local than non-local. And, well, all else being equal, we should have less determinism rather than indeterminism, or energy conservation and energy non-conservation. And if you answer what the justification is for this, sounds pretty intuitive, but so it's not, we cannot say anything more. I'm skeptical of this, but I don't think we can have much of a debate there. But my So that's why very motivated my follow-up to myself is it seems to me that like the methodology here, it seems to me that we should have a better methodology than arguing about merely possible cases and using this kind of very rational criteria. So I want to ask you something about the methodology you follow. So my suggestion was, well, you look at what the law says and what kind of quantities, mathematical quantities appear in laws, the simplest logic and right, and then you think what those must represent is the best device we have. You obviously don't think that's the right way to do it. So you think that sometimes the best laws we can have, we will have some mathematical fiction that doesn't represent directly anything. The real quantities are constructed in terms of that, but they don't represent. The question is, why not use this move more widely? Maybe that's exactly what you want to do. Say, I don't know, having a space-time manifold that creates problems with the whole argument and it's kind of indeterminism. So I would just take the laws as they are, I won't reformulate the theory at all, but I would just say, well, I will take the manifold not to represent anything, just to be a mathematical fiction. I mean, would you just liberally do that anytime you have a problem? You just say, well, that's not real, that's not real, that's not real.
So, if you take away the manifold, don't you take away too much, right? Okay, can you still make sense of the theory once you do that? That would be it seems to be a trade-off,
well,
right?
take away the manifold, I still have, suppose I have material bodies or something like that. All the evidence is just the distance between the bodies, right? But that would just be a lazy relationism to say, well, the manifold is just mathematical fiction. Then everything behaves as if there were a manifold. But I don't need to reformulate the theory without mentioning the manifold. Do you think that would be a sound strategy? Would it make things too easy?
So, for example, this relationism thing, I mean, there's again drawbacks, right? Because if you have some straightforward relationist metaphysics, something like Leibniz, then simply you kind of admit more symmetries than the laws, which are well experimentally confirmed, have. That seems to be the problem for Leibnizian metaphysics in general. So, yeah, when you're taking away structure, you need to be careful that you have kind of enough left to recover all that is well confirmed, right?
Sure, but I mean, it seems to me that you would have problems if you try to rewrite the laws and redo your physics only with what you have. And if you are basically an instrumentalist, it doesn't seem that. It seems to me that you could do it with everything without any. And as long as you can just explain what the evidence is, how it arises from what you do assume to exist, all the rest. You could.
If you're an instrumentalist, is that
well,
the
by
condition?
instrumentalism just means, well, you think that this is just a mathematical device that represents what my real ontology does, right? And that doesn't represent anything in the world. It seems to me that once you allow yourself to do that, there is no natural stopping point. I mean, you just a matter of taste. You can just do it all the way down and say, well, the fields maybe they're just some device that encodes in a convenient way how my particles behave, only the particles are real. Or you do that space-time, later it's the device, mathematical stuff that represents, that encodes the distances of my clock measure or whatever. And it seems to me like once I allow myself to do that, I can just do that.
In that case, I think indeed we would be embarked on a different project. I didn't say this, but kind of my presupposition or my general presupposition is to look at the theory and find kind of a charitable realist reconstruction or realist story which we can tell about the theory. And I think instrumentalists wouldn't be interested in debating ontology at all. I think,
but maybe the just thing I would say is that from my view you're already an instrumentalist because you look at the equation at the Hamiltonian, you say, oh, let's forget about that. Just the tool doesn't represent anything. And my question is that you've already done that or something. So you're already a bit of an instrumentalist. And I don't see why, the slippery slope, why not do that? Once you allow that to do that, what is the rationale not to do that with fields as well, with that stuff?
are you asking what is the motivation for being realist towards science, or?
Well, because you're not really a realist. You're a realist about something, not about anything.
Exactly.
Is there like a principle behind this?
Oh, general principle. I mean, I agree that it's just a fine-grained thing, right? I mean, you look at specific cases, you try to make a distinction, try to understand what is physical, what is unphysical. That's what seems to be the project of philosophy of physics in general.
Yeah, just a quick follow-up. I mean, his point is a bit that of a slippery slope for any kind of qualified or selective realism, right? But for instance, in the context of structural realism, right, which is also a form of qualified realism, you have a good criterion why you just care about structure. Namely, you want to account for that there's change of theories, and so you just commit to structure because it seems to be the thing which gets conserved over theory change. For instance, that would be an example for how you could be a selective / qualified realist without being on the slippery slope, floating on the down. And also, I think for this kind of program here, you can make up some general principles he has been using, but of course, you would like him to spell them out, I suppose.
Yeah. So one suggestion would be, which I think maybe is consistent with what you said so far. The idea would be, on average, we want to be realists. So if we see some quantity in the laws, all else being equal, we will think that it is real, that it represents something equal. Except if by doing so we violate some other constraint, like well, it introduces indeterminism, or then we have energy non-conservation, or we have some principle like this. So in those cases, then we will treat it as a mathematical feature, as a mathematical device doesn't represent. If by assuming that it represents, we have, would that be how you would move it?
No, well, I'm not sure. I mean, arguably, all else being equal, you want to have less structure, right? So maybe you want to cut out as much as possible on some kind of Occam's principle. So I'm not sure. Yeah.
Well, I mean, if you go that way, I think you will end up. It's a very interesting example. It's a cautionary example. You will end up like Michael Esper. He just allows himself to cut anything.
Is that a word?
The interesting thing is that I think it's a reduction ad absurdum of the kind of approach where you just, if you don't like something, you just say it's not real, it's a mathematical, just a means of representation, right? And it doesn't represent anything. And the point is that if you have no principle, and your principle is like economy, and you have the right to cut, then you will end up with nearly nothing at the end of the day. So the principle cannot be, I can cut whatever I want, and also I need to be as parsimonious as possible. Then you won't have fields, you won't have F-field realism, you won't have space-time, you won't have plenty of stuff. That all will be cut like the potentials. So if you need to stop the principle, like why should I retain fields? I mean, if I just allow to.
So I mean, simple. How would you explain electromagnetic phenomena without having the fields as real entities?
I understand I will explain without the potentials because I cannot literally use the laws.
So you can have one of them, right? But surely you need at least one of them.
Well, if you have any phenomenon that you cannot describe, that you cannot predict using the classical equations, you need to quantum mechanical description to explain what that is. And it mentions the potentials. I have no idea how you explain that without being realist about the potentials. What you could say, oh well, the things happen as if there were potentials, but there are no potentials. It doesn't seem to be really an explanation of what goes on. So I'm not for eliminating the fields. I'm just for keeping the potentials.
Interesting. Well, I mean, so in quantum mechanics specifically, as you said, changing potential to a gauge equivalent configuration, all that does is change the phase of the wave function, right? Global phase. So it's change in the classically, or unobservable distinction between the potential yields, unobservable distinction between the wave functions. And so then maybe, yeah, you just take some kind of equivalence class in both cases, something like that.
Niels, another follow-up?
Yeah, just Lorenzo's follow-ups to his follow-ups.
But not a quick one?
Yeah, kind of, yeah. So I'm just thinking that, typically you have this slippery slope situation and so on, you could say, blah, blah, blah. There are certain ways to stop it, let's say selective realism one, but maybe he really just wants to have, like a proper realism, package deal kind of realism, but then there's certain things which you just cannot commit to even if you want to do a package deal. Because certain things are just not well-defined, let's say. And for instance, one thing is not well-defined, the solenoid. Maybe not to speak just in the context of one specific theory, but in the whole package overall of all the theories that take together. I mean, what is a solenoid? For solenoid, we just learned solenoid would come along with infinite resistance. What do you need to support an infinite resistance? You need to have, I don't know, all kind of infinite constants probably to still have a current, or you need to have infinite current strength, but all these kind of things, right? So can't you just say, at least with respect to that kind of discussion, this Leibniz metaphysical discussion, that, so to speak, a part even a package deal realist can accept, as so to speak, as a natural way how I need to refine my realism, what I commit to, without ever setting me on a slippery slope. I don't need further general principles now to say what else I exclude. Because I'm really just minimally discussing what I need to commit to, not to. I don't know, sorry, just a comment, maybe there's a comment here.
Sorry for taking out the discussion. we agree on your point anyway.
So it's about, I think from slide 20, maybe, no, 21, sorry. No, okay, sorry.
Earlier.
Well, sorry. This one,
Yeah.
sorry. So, from my very naive perspective, not knowing much about the physics that's going on here, so I have two questions about this. So the first is, as a kind of general principle that properties that then show up in the infinite limit, but really not before, that those are maybe only mere artifacts of the approximation and so on. I see the plausibility, I guess, if it's something that can actually approximate. So for example, if the infinite has for something, I don't know, x equals 1000, and then you would maybe want some kind of approximation to this one. But if it's some kind of on-off thing, so if there wouldn't even be any way really of this approximating this, then I'm not that sure anymore when I find this all that plausible. Now I don't know if there's any way in which non-locality could be approximated. But if not, then I'm just not that sure anymore that I find this as plausible, because there is if there's no way of approximating that we could even see, then yeah. And the other thing is that then I was wondering, so how does this now relate to the argument against the physical possibility of the world, which was based on general properties of the infinite models? Because couldn't one then also do the same, if it's really this generally formulated, couldn't one say, well, I also say this about the determinism of the infinite model and the other property of the infinite model that was mentioned, and arrive at the conclusion that these are also just artifacts of the approximation. So as I said, from my very naive standpoint, probably for some reason can't, but then these two arguments would kind of weaken each other in some sense, potentially, if that were the case, if one could make this kind of application.
So, with your first point, if there was some kind of alternation, that would mean that there would be no limit, right, to reach in the end. I think that's what I took you to be saying, either for the properties or for the systems themselves. If the systems don't have a limit, then there is simply no idealization. And yeah, there is no idealization to speak of. We cannot approximate by using that system. If there is, sorry, is that?
Sorry, I think what you meant is that it's an on-off property.
Yeah, exactly. That's what I meant. So it's an on-off property, and then maybe for all finite things it's 0, and then for the infinite it's 1.
Yes, the idea is not that for the sequence it alternates, but the fact that it's an on-off property
Yeah, exactly,
It would be a very different thing if for 10,000 it would be a little bit non-local, and for 100,000 meters it would be a bit more non-local.
Exactly. But this is not something
that's not
you.
what's happening.
Yeah, but that's probably not something you could reasonably expect to, right? Because that's just not. But then, so why rule out that this kind of on-off property appears? If it was something that could be approximated, then I see why I would want to demand that it should be approximated. But if it's something that just cannot be approximated, yeah.
I'm still not quite sure I understand the on-off thing. Or, yeah.
So, if I understand it correctly, it's just that the non-locality, if you have this sort of a sequence of ever longer solenoids, I guess Pn, that's locally in the incoming particles. So for any finite n, it's going to be local. If you go to 100,000, a million, 10 million, a billion, whatever, always local for any finite number. And really only at the infinite limit it changes to non-locality. That, I think is a good reason to reject that switching on at the end as an artifact.
No, yeah, actually, yeah. So the thing is, no. So, yeah, maybe because I think my second point, maybe I would be more interested to hear you say about it, but just as a last attempt to make this clear. So, for some properties where we can actually have an approximation, right? I think it would be indeed very weird if suddenly in the limit, maybe they are there in time, whatever, and before at every step not. Because maybe it seems more reasonable that one would slowly approximate this. But for properties for which just no notion of approximation is to be had,
that's for example,
as for the non-locality, I guess. Then maybe we don't need to require this because requiring it wouldn't really make that much of sense.
There is a sense in which the sequence of properties approximates something, right? There is a limit of that sequence.
But approximating non-locality, so being a bit more non-local. Well then, all the better. Then, okay.
Sorry, it approximates. The truth value of this proposition is true. It tends to true or something like that. So, yeah. The problem is that if you look at the property of the infinite systems, of the infinite system independently, it comes out false. So there's a mismatch between what the sequence tends to and what the actual property of the infinite system is. And I agree, that's pathological. And I think we agree on that. Or?
I'm not sure about it. Let's leave it at that.
It seems to me as well that you agree.
And maybe to your second point, indeed I think we definitely should generalize this and maybe think that even the treat with suspicion infinite models, or rather treat with suspicion the possible worlds naively kind of interpreted from these models, definitely.
Yeah, I have a number of clarificatory questions. I don't know whether you want to
We're almost out of time, but maybe
okay.
you should start with one or two, or?
Yeah, so then if you could just suggest one that may be short, if you could expand a bit on why do you think that as infinite potentials tend to create discontinuity, the first derivative of the wave function, then this is something for which we should rule them out as physically possible?
That's, yeah. Well, arguably, we can measure the wave function. We can measure perhaps even the first derivative of the wave function or something like that. So it would seem strange to see some kind of discontinuity if we actually carried out that experiment, or yeah, it seems hard to imagine how that would play out to me. But seems that we never really observe discontinuities actually, right, in experiments.
Okay, okay. Yeah. Yeah, I was wondering whether that is enough to rule it out as a physical possibility, but okay. Yeah.
But certainly, I mean, discontinuities occur all over the place, right,
Yeah,
in physics.
Yeah, right, exactly.
But yeah, I guess usually it would be signifying that we don't have a complete description or something like that. But I perhaps treat them as approximations. Yes, but.
Okay.
Like potential well, I mean, that would be a typical example, right, where you have infinity. So it's kind of common in a way, but then you're saying it's not a.
Sorry, potential well and the wave function in a potential well, or.
Yeah, don't you have an infinite potential?
Infinitely deep potential well?
Yeah.
I guess.
Yeah, I mean, it would be.
Right, exactly. That would be discontinuity in the first derivative, yeah. I guess maybe once again we could launch this formal argument where perhaps we would like to kind of naively admit only certain mathematical functions as kind of being genuine possibilities, and yet perhaps discontinuous functions are kind of pathological. But yeah, maybe that's a little too strong. Yeah, maybe that's a little too strong for actual physics. Yeah, I don't know.
I thought it was completely strong.
One more?
Yeah, okay, yeah, why not? If you could expand a bit, because I do know the physics about this, how the toroidal version of the Aharonov-Bohm model is connected to this idea of the infinite solenoid case.
Yes, so, well, I don't have a picture, but it would look basically, I think, exactly the same as the picture I gave here.
But yeah.
But the solenoid would be toroidal or something like that. I guess okay, this might be a little controversial with the people who write on the idealization debate, but I guess the key here would be again like the non-simple connectedness of the space, because the torus again would present some kind of non-trivial topological complication, and I guess if I subscribe to the topological explanation, I would say that explains why the Aharonov-Bohm pattern changes.
Okay.
But yeah, as I say this, I mean the topological explanation is controversial in this literature. So yeah.
Okay. Please join me in thanking Matěj.